So let's take a look at how to find the remainder estimates for both the integral test and the alternating series test. And so starting off with the integral test, let's say we have the integral, or the infinite series, of a sub n. Now a sub n the series of a sub n must converge in order to find the remainder. And so if it converges, let's say a sub n is equal to f of x. Now in order to find the remainder is basically going to be the integral of n plus 1 to infinity of f of x, or a sub n, dx, must be less than or equal to the remainder r sub n, and the remainder must be less than or equal to the integral from n to infinity of f of x dx. So the remainder must be in between the integral from n plus 1 to infinity and the integral from n to infinity of f of x dx. But really what we need to focus on is the right half of the inequality. We just need to know that the remainder must be less than or equal to the integral from n to infinity of f of x dx, or a sub n. So for number 1, we have the series from 1 to infinity of 1 over n squared, and we need to find the value for n to make sure the error is less than 1 over 1,000, or 0.001. And so in order to find the remainder, we must make sure the series converges, and it does converge by the p-test since 2 is greater than 1. And so we need to change the variable and take the integral of it now. So if 1 over n squared is our f of x, then we can basically take the integral of it and evaluate. So we get the integral from, once again, we're going to go from n to infinity of 1 over n squared. And instead of n, I'm going to write x dx. So 1 over x squared dx. So I can change it to the integral of x to the negative second. So then we get x to the negative first over negative 1. So then we get negative 1 over x. And then so when we evaluate, we're going to go from n to infinity. So then when I plug in infinity, we basically get negative 1 over infinity, or 0, minus, when I plug in n for x, we'll get negative 1 over n. So minus a negative 1 would be plus 1 over n. So then we get 1 over n as the integral. Now we need to make sure whatever we plug in for n, it needs to be less than 0.001. So I'm going to set 1 over n less than 0.001. And so I can go ahead and just swap these two places. So then we'll get 1 over 0.001 must be less than n, or in other words, n has to be greater than 1 over 0.001 or 1,000. So now moving on to the alternating series test. In order to calculate the remainder for the AST, let's say we have the infinite series of an alternator, negative 1 to the n, times a sub n. Now similar to the integral test, we need to make sure that this series converges first, then we can find the remainder. And so the remainder theorem for the AST states that the absolute value of the sum minus the partial sum is going to be equal to the absolute value of the remainder, and the absolute value of the remainder is going to be less than or equal to a sub n plus 1. And so really we don't even need to focus on the sum minus the partial sum. All we need to focus on is the remainder being less than or equal to a sub n plus 1, or the absolute value of the remainder. So for number 2, we have to find how many terms do we need to add in order to find the sum to the indicated accuracy. So we're given the infinite series from 1 to infinity of an alternator, negative 1 to the n minus 1 over n squared, and the absolute value of the error must be less than 0.01 or 1 over 100. So the first thing we need to make sure is that the series converges. So ignoring the alternator, we have 1 over n squared, and so the limit as n approaches infinity of 1 over n squared is equal to 0, and since it's equal to 0, we know it converges by the AST. So because it converges, we can use the remainder theorem here, and so ignoring the alternator, 1 over n squared is going to be our a sub n. So we need to find a sub n plus 1. So all we're going to do is replace n with n plus 1. So a sub n plus 1 is going to be equal to 1 over n plus 1 squared. And so once again, the reason why we can take away the alternator is because we're taking the absolute value of the error, or the remainder. When we take the absolute value, we can automatically get rid of the alternator. And so now what we do is we take what we have for a sub n plus 1, and we set it less than 0.01 because that is our desired error bound here. So 1 over n plus 1 squared must be less than 0.01, whatever we plug in for n. And so I can go ahead and switch the places of n plus 1 squared and 1 over 100. So when I do that, we get 1 over 0.01 must be less than n plus 1 squared. 1 over 100, 1 over 1 over 100 is basically 100. So we'll get 100 must be less than n plus 1 squared. Now if I take the square root of both sides, we get 100, or 10. The square root of 100 is 10, must be less than n plus 1, which means if we subtract over 1, 9 must be less than n, or n must be greater than 9. Now if n must be greater than 9, which means we need to go one term up, so n must be equal to 10. So we need 10 terms to find the sum to the indicated accuracy of the error of less than 0.01. So now for number 3, we have the series from 1 to infinity of negative 2 to the n over n factorial, and we need to make sure the error, the absolute value of the error or the remainder must be less than 0.01. So once again, the first step is to make sure that the series converges. So I can actually separate negative 2 to the n into negative 1 to the n times 2 to the n, and then over n factorial. So when I take the limit, I can get rid of the alternator when we do the AST. So we get the limit as n approaches infinity of 2 to the n over n factorial. Now n factorial grows faster than 2 to the n, so our limit will be 0, which means it does converge by the AST. Now when we get rid of the alternator here, our a sub n is going to be equal to what we have that we set the limit to, 2 to the n over n factorial. And so a sub n plus 1 is going to be equal to 2 to the n plus 1 over n plus 1 factorial. Since the error needs to be less than 0.01 or 1 over 100, we're going to set that less than 0.01. And so when it comes to these types of problems, you can basically just guess and check by plugging in different values. Let's just go ahead and plug in first n equals 6. So when I do that, and plug in n equals 6, we basically get 2 to the 6 plus 1, or 2 to the 7th, over 6 plus 1, 7 factorial, which gives us a value of around, when I plug into my calculator, I get 0.025. 0.025, we set that less than 0.01, and notice that is not less than 0.01, so we had to try a different n value. So this time I'm going to go ahead and try n equals 7 instead of 6. So when I do that, we'll get 2 to the 7 plus 1, or 2 to the 8th over 8 factorial. And so that gives us around 0.006. And 0.006 is obviously less than 0.01. So we do need 7 terms to find the sum to the indicated accuracy of less than 0.01.